January 20th, 2025. Hefei, China. A control room lit by screens showing a single number climbing past 1,000 seconds. Inside a massive steel ring 3 stories tall, plasma burns at over 100 million degrees Celsius, 6 times hotter than the core of the sun, and it refuses to go out. The clock hits 1,066 seconds, 17 minutes and 46 seconds of sustained fusion. That is not a simulation, not a concept. It is a world record that just made every other fusion lab on Earth recalculate their timelines. This is the East Tokamak, experimental advanced superconducting tokamak, the machine the West barely talks about, and it just did what ITER spent $28 billion trying to prove was possible. You need context for what just happened. Fusion reactors have been hitting high temperatures since the 1990s. ITER's predecessor, JET, reached 100 million degrees back in 1997. Temperature was never the bottleneck. The problem was always time. Plasma is the 4th state of matter, hotter than gas. A soup of stripped electrons and nuclei that wants to escape any container you put it in. To fuse hydrogen into helium and release energy like the sun does, you need to hold that plasma in a magnetic bottle at absurd temperatures for long enough that fusion reactions outnumber the energy you pump in. Most reactors measure their burn time in seconds, single-digit seconds. The previous world record was 403 seconds, also held by East, set in 2023. East just multiplied that by 2.6 in 2 years. Here is where you drop a comment telling us where in the world you are watching from and what time it is there right now. And subscribe if you are new. This is where the most extraordinary stories come alive. Because what East just demonstrated is not incremental progress. It is the moment fusion shifted from a physics experiment to an engineering problem. The difference between those two is the difference between proving something can happen and building a machine that does it reliably. Every minute of sustained plasma is another data point on stability, on controlling instabilities, on what happens to materials when they sit next to a miniature sun for a quarter of an hour. The West is still optimizing for peak performance. East is optimizing for endurance. And endurance is what a power plant needs. Rewind to understand why temperature records are a distraction. The sun fuses hydrogen at 15 million degrees in its core. Gravity does the heavy lifting. On Earth, we have no gravity well to squeeze atoms together, so we compensate with heat. Way more heat. East runs at over 100 million degrees, 7 times hotter than the sun's core. At those temperatures, hydrogen isotopes, deuterium and tritium, slam into each other hard enough to overcome electromagnetic repulsion and fuse into helium. The reaction releases a neutron and a flood of energy. That energy heats a blanket surrounding the reactor. The blanket heats water. The water spins a turbine. The turbine generates electricity. That is the theory, but only if the plasma stays lit long enough to matter. The tokamak is a Russian invention, a toroidal chamber where magnetic fields trap plasma in a donut shape. East is a superconducting tokamak. Its magnets are cooled to near absolute zero, so they can generate field strengths powerful enough to confine plasma at solar core temperatures without melting. The challenge is not creating the plasma. You can do that with a microwave oven if you are reckless. The challenge is confinement. Plasma wobbles. It develops instabilities, edge-localized modes, disruptions. Any wobble that touches the wall kills the reaction and can damage the reactor. Holding stable confinement for 17 minutes means East's control systems are reacting to instabilities in real time and correcting them faster than the plasma can escape. That is the breakthrough. Not the heat, the control. East is run by the Institute of Plasma Physics at the Hefei Institutes of Physical Science, part of the Chinese Academy of Sciences. Construction started in 2000, first plasma in 2006. For nearly 2 decades, it has been a testing ground for advanced confinement modes. H mode, high confinement mode, a regime where the plasma edge forms a transport barrier that keeps heat and particles from leaking out. H mode is essential for a commercial reactor because it dramatically improves energy confinement time. The problem is, H mode is unstable. It invites edge-localized modes that can dump massive heat pulses onto the reactor wall. East has spent years learning how to sustain H-mode plasma without destroying itself. The 1066-second burn was in H-mode, steady state, long pulse. That combination is what a power plant needs. Here is the curve that matters. East hit 403 seconds in 2023. That was already the world record. 2 years later, it reaches 1066 seconds. That is not a linear improvement. The jump from 6.5 minutes to 17.5 minutes is a 2.6x multiplication. Exponential learning. The time between records is shrinking. The magnitude of each record is growing. This is the signature of a technology approaching viability. Compare that to the International Fusion Roadmap. ITER, the $28 billion international tokamak under construction in France, is designed to achieve 400 to 600 second burns when it goes online in the 2030s. East is already past that. ITER's timeline assumes steady incremental gains. East just demonstrated a step change. The Western fusion establishment has a specific narrative. Fusion is always 30 years away. Progress is slow. Breakthroughs are incremental. East does not fit that narrative. It is operated by a country the West spent decades assuming was catching up. The assumption was China would follow the roadmap laid out by American and European labs, build smaller machines, learn the basics, eventually contribute to international projects. Instead, China built East and started solving problems everyone agreed were a decade away from being solvable. The 1066-second burn is not a fluke. It is the result of sustained investment in superconducting magnet technology, plasma control algorithms, and materials science that can withstand prolonged neutron bombardment. East is not catching up. It is pulling ahead. There is a technical detail that separates hype from reality. Fusion reactors talk about Q, the ratio of energy out to energy in. Q equals 1 means break even. You get as much energy from fusion as you put into heating the plasma. Q greater than 1 means net energy gain. A reactor that can sustain Q greater than 1 for hours at a time is a power plant. East has not published Q values for the 1066-second burn yet. That number will determine whether this is a scientific milestone or an engineering one. But here is what we know. East was running in steady-state H mode. That is the regime where Q approaches viability. The previous 403-second burn was focused on control, not optimization. The new record suggests they are moving from proving it can be done to proving it can be done efficiently. What East actually solved is the stability problem. Every previous long pulse attempt ran into the same wall. Plasma instabilities grow over time. The longer you run, the more likely a disruption ends the shot. Disruptions are catastrophic. The plasma loses confinement in milliseconds. Magnetic energy dumps into the reactor wall. If you are unlucky, it cracks components that take months to replace. East's achievement is keeping the plasma stable for over 1,000 seconds without a single major disruption. That requires feedback control systems that measure plasma conditions thousands of times per second and adjust magnetic fields, heating power, and fueling rates in real time. It requires predictive algorithms that see instabilities forming and suppress them before they grow. This is machine learning applied to plasma physics. And it works. The economics start to look different at this time scale. A reactor that burns for 17 minutes continuously is not producing electricity yet. But it is proving that continuous operation is possible. A commercial fusion plant needs to run for hours, days, weeks between maintenance shutdowns. Each shutdown costs money. Every hour of downtime is lost revenue. East's burn time is still far from commercial viability, but the gap is closing faster than the official roadmaps predicted. If the learning curve continues at this rate, sustained operation measured in hours is not decades away. It is years away. That timeline threatens assumptions. Western fusion projects are betting on a slow, steady path. East's trajectory is steep, and steepness changes everything. Now the obstacle's still standing. East runs on deuterium-deuterium fusion, DD fusion. It produces fewer neutrons than deuterium-tritium fusion, but it is easier to sustain. A commercial reactor will likely run on DT fusion because it has a higher energy yield. DT fusion is harder. Tritium is radioactive and scarce. You have to breed it inside the reactor using lithium blankets. Those blankets have never been tested at scale in a tokamak. East's success with DD fusion does not guarantee success with DT, but it proves the control systems and confinement techniques work. The next step is integrating tritium handling and blanket technology. That is an engineering challenge, not a physics one. And engineering challenges have solutions. Physics challenges sometimes do not. The other problem is the wall, neutrons. High-energy neutrons stream out of every fusion reaction and slam into the reactor's inner surface. Over time, those neutrons displace atoms in the metal. They create voids, embrittlement, swelling. The material degrades. At some point, the wall has to be replaced. Current tokamak wall materials last a few years under neutron bombardment before replacement is necessary. A commercial reactor needs walls that last decades. East's 17-minute burn produced a tiny fraction of the neutron dose a power plant would generate in a day. The materials problem is still unsolved. But again, it is engineering. There are candidate materials, tungsten alloys, reduced activation steels, SiC composites. Testing them requires a reactor that runs long enough to accumulate meaningful neutron exposure. East is now that reactor. What happens when you cross 1,066 seconds is you enter a new testing regime. You can study plasma behavior over timescales that matter for real operation. You can validate turbulence models. You can measure how impurities accumulate. You can test whether your heating systems can maintain temperature without overheating components. You can push on edge stability limits and see what breaks first. Every minute of sustained plasma is a stress test for every subsystem. Magnets, cooling, diagnostics, power supplies. Control algorithms. East is now the world's longest-running continuous fusion experiment. That makes it the world's best platform for answering the questions that determine whether fusion becomes a power source or stays a curiosity. And China is not sharing all the data. There is a geopolitical angle no one wants to say out loud. Fusion is strategic. The country that commercializes fusion first gains an energy advantage that could last a century. Unlimited clean baseload power changes industrial competitiveness. It changes military capability. It changes which nations can afford to desalinate water, manufacture synthetic fuels, and run energy-intensive industries without carbon emissions. The West has treated fusion as a scientific project. Important, but not urgent. China is treating it as a national priority. East is one part of a broader fusion program that includes the HL2M tokamak, the Hefei conceptual reactor, and partnerships with ITER. The investment is measured in billions. The timeline is measured in years, not decades. And the message is clear. Fusion is not 30 years away. It is arriving. And it might not arrive in California or Provence. A reactor that holds plasma for 17 minutes and 46 seconds does not power a single light bulb yet. It does not feed energy into a grid. It does not solve climate change. What it does is start a clock. Every lab working on fusion now has a benchmark to beat. Every timeline that assumed Chinese fusion was 5 years behind needs revision. East proved that long-pulse, steady-state H-mode confinement is achievable. Not in theory, in practice, on hardware, with control systems that work. The next question is how fast the gap closes between 1,066 seconds and continuous operation. If the curve holds, that answer comes sooner than anyone expected. The future of fusion was not supposed to be decided in Hefei, but that is exactly where the clock is running fastest. Subscribe and turn on notifications. The next breakthrough out of China makes this one look like a warm-up. Would you trust a fusion reactor built in China to power your city? Drop your answer below. We read every one.